The cosmos, as we perceive it, is a breathtaking tapestry of light. Galaxies, like jeweled islands, drift through an ocean of profound blackness. Nebulae, the stellar nurseries, bloom with incandescent colors, birthing stars that will blaze for billions of years. Quasars, the most luminous objects known, pierce the darkness from the very edge of the observable universe. This is the cosmos of light, the universe we see, the universe we have charted and celebrated. Yet, this brilliant spectacle, this grand and glorious display, is a mere facade. It is the visible froth on an ocean of unimaginable depth and darkness. For every point of light, there are volumes of space so vast, so seemingly empty, that they defy comprehension. We call this emptiness the void. For centuries, we assumed it was just that, a desolate, silent gap between the places where matter had chosen to congregate. But a revolution in our understanding is underway. Armed with new eyes, new theories, and an insatiable curiosity, we are beginning to peer into that darkness. And what we are finding is not emptiness. We are discovering a hidden universe, a phantom cosmos of structures so vast, so faint, and so massive that they dwarf everything we can see. This is the story of that hidden reality. It is the story of the cosmic web, the dark halos, the ghost galaxies, and the profound realization that the majority of our universe has remained, until now, completely invisible. To understand this invisible architecture, we must first zoom out, far beyond the confines of our own Milky Way galaxy, past our local group of galaxies, past the Virgo supercluster, to the largest scales imaginable. From this vantage point, the distribution of galaxies is not random. They are not scattered like dust motes in a sunbeam. Instead, they trace a magnificent, intricate pattern, a web-like structure of unbelievable proportions. This is the cosmic web. It is the fundamental skeleton of the universe. Computer simulations of cosmic evolution, fed with the known laws of physics and the ingredients of the early universe, consistently produce this structure. Gravity, acting over billions of years, is the master weaver. In the beginning, the universe was almost perfectly smooth, a hot, dense soup of particles and energy. But there were minuscule, quantum-level fluctuations in density, tiny areas that were infinitesimally denser than their surroundings. Over eons, gravity amplified these tiny imperfections. The slightly denser regions pulled in more and more matter, while the less dense regions became emptier and emptier. The result is the cosmic web we see today. The brightest parts of this web, the glittering intersections where the threads come together, are the great galaxy clusters. These are the cities of the cosmos, gravitationally bound collections of hundreds or even thousands of galaxies, all swimming in a vast sea of superheated gas. The threads connecting these cities are known as filaments. These filaments are colossal structures, stretching for hundreds of millions of light years. They act as cosmic superhighways, funneling gas and dark matter from the voids into the clusters, feeding the galaxies within them and fueling the birth of new stars. And then there are the voids themselves. These are the vast, underdense regions that make up the bulk of the universe's volume. They are not entirely empty, but the density of matter within them is a tiny fraction of what is found in the filaments and clusters. The profound truth of the cosmic web is that most of it is invisible. The galaxies we see are merely the lighthouses, the luminous beacons that trace the densest parts of the web. The filaments themselves, where the majority of the universe's ordinary matter is thought to reside, are almost entirely dark. This matter is primarily composed of primordial hydrogen and helium, forged in the Big Bang. It is too thin and too diffuse to collapse and form stars on its own. It is a tenuous, transparent gas, a cosmic fog that does not glow. For decades, the existence of these filaments was a theoretical certainty, but an observational nightmare. How can you see something that emits no light? The breakthrough came from using the universe's own background lighting. Astronomers targeted quasars, the intensely bright cores of distant active galaxies. As the light from a quasar travels across billions of light years to reach our telescopes, it passes through the cosmic web. When the light beam intersects a filament of intergalactic gas, the hydrogen atoms in that gas absorb specific frequencies of the quasar's light. By analyzing the spectrum of the quasar's light when it arrives at Earth, astronomers can see these absorption lines, tiny dark gaps in the spectrum. Each gap corresponds to a cloud of hydrogen gas at a specific distance along the line of sight. This technique, known as studying the Lyman alpha forest, provided the first concrete evidence that these vast, dark rivers of gas truly existed. It was like detecting a trail of invisible ink by shining an ultraviolet light on it. More recently, technology has advanced to the point where, under perfect conditions, we can begin to directly image the faint glow of these filaments. The hydrogen gas, while not forming stars, is not completely inert. It is heated and energized by the radiation pouring out of the galaxies embedded within it. This causes the gas to emit a very faint, diffuse glow. Using extremely sensitive instruments on the world's largest telescopes and stacking hundreds of hours of exposure time, astronomers have captured the first ghostly images of these cosmic threads, confirming that galaxies are not isolated islands, but are connected parts of a single, coherent, gargantuan structure. This skeleton, woven from dark matter and traced by nearly invisible gas, is the first layer of the phantom universe. It is the framework upon which everything we see is built. To explore the next layer of this hidden reality, we must zoom back in, from the intergalactic scale to the scale of an individual galaxy like our own Milky Way. When we look at a spiral galaxy, we see its bright central bulge, its graceful star-studded arms, and its glowing disk. We can measure the stars, count them, and calculate the galaxy's total visible mass. From this, using Newton's laws of gravity, we can predict how fast the stars in the outer regions of the galaxy should be orbiting the galactic center. The logic is simple. The farther a star is from the bulk of the mass at the center, the slower it should move, just as Neptune orbits the Sun far more slowly than Mercury. In the 1970s, astronomer Vera Rubin performed these very measurements, and the results were completely astonishing. They broke the laws of physics as we knew them. The stars in the outer parts of galaxies were not slowing down. They were moving at the same high speed as stars much closer to the center, and in some cases even faster. The galaxies were spinning far too quickly. According to the visible matter, they should have flown apart, with their outer stars flung out into intergalactic space. The only possible explanation was that there was a vast amount of unseen mass, a gravitational glue holding these galaxies together. Its gravitational pull was what kept the rapidly orbiting stars in check. This mysterious substance was dubbed dark matter. It is called dark, not because it is black, but because it is completely transparent. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is detectable only through its gravitational influence on the matter we can see. Subsequent observations, from the movements of galaxies within clusters to the temperature fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, have all confirmed its existence. The universe, it turns out, is a strange recipe. All the normal matter, the stuff that makes up stars, planets, and ourselves, everything made of atoms, accounts for only about 5% of the total mass and energy content of the cosmos. About 27% is dark matter. The remaining 68% is an even more mysterious substance called dark energy, which is responsible for the accelerating expansion of the universe. Dark matter is not just sprinkled evenly throughout space. Gravity has sculpted it. Just as the cosmic web forms the universe's skeleton, every individual galaxy, including the Milky Way, is thought to be embedded within a massive, roughly spherical cloud of dark matter. This is known as a dark matter halo. This halo is the true galaxy, The brilliant spiral or elliptical structure we see is merely the small luminous concentration of normal matter that has settled into the very center of this vast, invisible structure. The dark matter halo is the galaxy's gravitational backbone. It is the unseen scaffolding that dictated where the galaxy formed in the first place and continues to govern its every movement. The scale of these halos is difficult to overstate. The visible disk of the Milky Way is about 100,000 light-years across. Its dark matter halo, however, is estimated to extend for at least 1 million light-years, perhaps even 2. It is a colossal, invisible sphere, and we are living deep within it. The stars and gas we see are just the tip of a cosmic iceberg. This realization fundamentally changes our perspective. Our galaxy is not just a disk of stars. It is a complex, multi-component system, dominated by a substance we cannot see and do not understand. Mapping the shape and extent of these invisible halos is one of the great challenges of modern astronomy. One of the most powerful tools we have is a phenomenon predicted by Albert Einstein's theory of general relativity, gravitational lensing. Einstein showed that massive objects warp the fabric of space-time around them. Light, which normally travels in a straight line, will follow these curves in space-time. This means that a massive object, like a galaxy cluster or a dark matter halo, can act like a cosmic telescope, bending and magnifying the light from a more distant object that lies directly behind it. When the alignment is perfect, the background object's light can be smeared into a ring, known as an Einstein ring, or split into multiple distorted images. By studying the precise way in which the background light is warped, astronomers can work backward to calculate the mass of the foreground object and map the distribution of that mass. Crucially, this technique is sensitive to all mass, both normal and dark. Gravitational lensing has allowed us to create detailed maps of dark matter in distant galaxy clusters, revealing vast, clumpy distributions of the invisible substance that perfectly match the predictions of our models. It provides unambiguous proof that these invisible halos are real, massive, and are the dominant gravitational component of these cosmic structures. Furthermore, our cosmological models predict that the formation of a large dark matter halo is not a smooth process. It grows through a series of mergers and acquisitions. Over billions of years, a large halo, like the one surrounding the Milky Way, gravitationally pulls in and eats smaller dark matter halos in its vicinity. While the normal matter of these consumed dwarf galaxies, their stars and gas, can be ripped apart by tidal forces to form long stellar streams, their dark matter cores are much more resilient. The models predict that a large halo should be teeming with hundreds or even thousands of these smaller orbiting subhalos. These subhalos are the ghostly remnants of the galaxies our Milky Way has cannibalized throughout its long history. They are, in essence, phantoms of the past, still orbiting within the larger invisible structure. Finding and studying these subhalos is a key test of our model of cosmic structure formation. However, if these subhalos contain few or no stars, they would be completely invisible to conventional telescopes, presenting another layer of the phantom universe that we are only now developing the tools to search for. This brings us to the most literal and tantalizing of the cosmic phantoms, the ghost galaxies. These are not merely the invisible components of normal galaxies, but entire stellar systems that are, for various reasons, almost impossible to see. They exist at the very threshold of detectability, challenging our definitions of what a galaxy is. They fall into several fascinating categories. First are the low surface brightness galaxies, or LSBs. A galaxy's surface brightness is a measure of its light spread out over an area. Most galaxies we know, like Andromeda, have a high surface brightness. They are luminous and stand out clearly against the black background of space. LSBs, however, have a surface brightness that is fainter than the ambient glow of our own planet's night sky. They are incredibly diffuse, like cosmic smoke rings. For decades, they went largely undetected because our telescopes and photographic plates simply weren't sensitive enough to register their faint glow against the sky's background noise. We were biased towards finding the bright, easy targets. The discovery of the archetypal LSB, Malin 1, in 1986, was a shock to the astronomical community. It is a monstrous spiral galaxy, potentially one of the largest known, but its disk is so faint and diffuse that it is almost completely transparent. The stars within it are spread so far apart that its existence seems tenuous. The discovery of Malin 1 and others like it revealed that our census of galaxies in the universe might be woefully incomplete. A significant population of massive, faint galaxies could be lurking in the dark, missed by all our previous surveys. These LSBs pose a puzzle. Why did they form this way? One theory suggests they formed in isolated low-density regions of the cosmic web, where they had less gas to fuel vigorous star formation, leading to a much more spread out and anemic population of stars over cosmic time. A more extreme and recently discovered class of phantom objects are the ultra-diffuse galaxies, or UDGs. As their name suggests, these galaxies are extremely faint and spread out. The startling thing about UDGs is their size. Many of them are as large as the Milky Way, spanning tens of thousands of light years, but they contain only 1% of the stars. Imagine taking a small dwarf galaxy and puffing it up to the size of a giant without adding any new stars. The result is a ghostly swarm of stars, so thinly distributed that you could look right through the galaxy and see the objects behind it with ease. The discovery of a significant population of UDGs by the Dragonfly Telephoto Array, an innovative telescope made of multiple telephoto lenses designed specifically to find these faint, extended objects, opened up a new frontier in astrophysics. The immediate question was, how do these galaxies hold themselves together? With so few stars for their size, their internal gravity should be incredibly weak. They should have been easily ripped apart by the tidal forces of any nearby massive galaxies. The answer, it was thought, must be dark matter. UDGs must be failed Milky Way-sized galaxies, objects that started with a massive dark matter halo but, for some reason, were extremely inefficient at converting their gas into stars. The dark matter halo would provide the gravitational glue necessary to keep their sparse star populations gravitationally bound. The UDG named Dragonfly 44 seemed to be a perfect example. Observations of the motions of its star clusters suggested it had a mass comparable to the Milky Way, meaning that about 99% of its mass had to be dark matter. It was a true dark matter-dominated ghost. But then a spanner was thrown in the works. Astronomers discovered other UDGs like NGC 1052 DF2 and DF4 that appeared to have almost no dark matter at all. This was a profound paradox. How can a galaxy-sized object with so few stars exist without the gravitational scaffolding of dark matter to hold it together? Its existence seemed to violate our understanding of galaxy formation. The finding is highly controversial, with some astronomers suggesting that the distance to these galaxies has been miscalculated, which would change the interpretation of their properties. Others propose exotic theories, perhaps involving unique gravitational interactions that expelled the dark matter. Whatever the final answer, these ghostly UDGs are forcing us to confront the gaps in our knowledge. They are proving to be cosmic laboratories for testing our theories of dark matter and galaxy evolution at their most extreme limits. This leads to the ultimate and most elusive prize in this cosmic ghost hunt, a true dark matter galaxy. This would be a gravitationally bound object the size of a galaxy, but composed almost entirely of dark matter, with virtually no stars or gas at all. It would be a halo without a beacon. According to our models of structure formation, these objects should exist. They would be the failed galaxies that formed from a dark matter halo but never managed to attract enough normal matter to ignite star formation. They are the subhalos, predicted to be orbiting our own Milky Way, that never hosted a dwarf galaxy. They are the ultimate phantoms of the void. Detecting such an object is an immense challenge. By definition, it emits no light. We could not see it with any telescope that detects photons, whether it be optical, infrared, radio, or X-ray. The only way to find a true dark matter galaxy is through its gravitational influence. One method is to search for subtle gaps or disturbances in the long, thin stellar streams that orbit the Milky Way. These streams are the tidal debris of dwarf galaxies that have been torn apart, and they trace smooth, predictable paths around our galaxy. If a massive, invisible subhalo of dark matter were to pass through one of these streams, its gravity would punch a hole in it, creating a detectable gap or ripple. Scientists are meticulously mapping these stellar streams with projects like the Gaia Space Observatory, looking for just such evidence of unseen perturbers. Another method is gravitational lensing, but on a much smaller scale. If a compact dark matter halo were to pass directly between us and a distant star, it could momentarily magnify that star's light in an event called gravitational microlensing. Searching for these fleeting events across millions of stars could, in principle, reveal the presence of a population of invisible halos. As of now, a definitive confirmed dark matter galaxy has yet to be found, but the search is intensifying. Its discovery would be a landmark moment in science, confirming a key prediction of our cosmological model and finally revealing one of the universe's most deeply hidden secrets. The quest to illuminate this phantom universe is being driven by a new generation of technological marvels, telescopes, and observatories designed with the specific goal of seeing the unseen and mapping the invisible. They are our new eyes, opening up a fresh perspective on the cosmos. The James Webb Space Telescope, JWST, with its enormous gold-plated mirror, is an infrared powerhouse. Infrared light can penetrate through clouds of cosmic dust that obscure visible light, and more importantly, it can see the most distant objects in the universe. Because the universe is expanding, light from very distant objects is red-shifted to longer, redder wavelengths. The light from the very first galaxies, which formed when the universe was just a few 100 million years old, has been stretched so much that it is only detectable as infrared radiation. JWST is designed to capture this ancient light. It is peering back in time to witness the cosmic dawn, the moment the first stars and galaxies ignited. By doing so, it can see the very first, faintest proto-galaxies as they begin to condense at the nodes of the primordial cosmic web. It can study the faint, ancient stellar populations of ghost galaxies in our local universe, dissecting their history and chemical makeup. JWST is providing the first baby pictures of galactic structures, showing us how the luminous universe first began to emerge from the all-encompassing darkness. While JWST focuses on deep, detailed views of small patches of the sky, the recently launched Euclid Space Telescope has a different mission. Euclid is a cosmic cartographer. Over its lifetime, it will survey 1/3 of the entire sky, creating a vast 3D map of the positions and shapes of billions of galaxies. Its primary purpose is to study the dark universe, dark matter, and dark energy. One of its key methods is weak gravitational lensing. Unlike the strong lensing that creates dramatic rings and multiple images, weak lensing causes tiny, almost imperceptible distortions in the shapes of background galaxies. A galaxy that should be perfectly circular might appear very slightly elliptical. By measuring these minute distortions for billions of galaxies over a vast area of the sky, Euclid's data can be combined to create a massive map showing the distribution of all matter, most of which is dark matter. This will be our most detailed chart of the cosmic web and its dark matter halos, revealing the invisible large-scale structure with unprecedented clarity and allowing us to test our cosmological models with incredible precision. On the ground, a new titan of astronomy is nearing completion in the Chilean Andes, the Vera C. Rubin Observatory. Its mission is the Legacy Survey of Space and Time, LSST. Every few nights, its enormous camera, the largest ever built for astronomy, will photograph the entire visible southern sky. It will repeat this process for 10 years, building up an incredibly deep, high-resolution image of a huge portion of the universe. But crucially, it will also create a time-lapse movie of the night sky. This will be revolutionary for detecting faint diffuse objects like UDGs and LSB galaxies. By digitally stacking years of images, the faint glow of these phantoms can be made to emerge from the background noise. Its time-lapse capability will also make it the ultimate tool for detecting transient events like supernovae and gravitational microlensing events, which could be the telltale signs of compact, dark matter objects passing in front of distant stars. Finally, we have the new frontier of radio astronomy, exemplified by the upcoming Square Kilometre Array, SKA, a network of thousands of radio telescopes spread across 2 continents. The SKA will be able to map the distribution of neutral hydrogen gas, the raw fuel for star formation, across cosmic history with astonishing sensitivity. This will allow it to directly image the tenuous gas in the filaments of the cosmic web in detail for the first time. It will be able to detect the faint reservoirs of gas that might surround dark matter galaxies, giving us another way to hunt for them. By charting the fuel of the cosmos, the SKA will provide a completely different view of the invisible structures that govern galaxy evolution. From the largest scales of the cosmic web down to the individual phantom galaxies lurking in the darkness, a new picture of the universe is emerging. It is a universe that is far more structured, more complex, and more mysterious than we ever imagined. The light we see, the brilliant galaxies and nebulae, are not the main story. They are merely the decorative elements on a vast invisible architecture that dominates the cosmos. This phantom universe, composed of dark matter and traced by tenuous gas, is the true reality. It is the framework whose gravity dictated the destiny of all that we can see, guiding the flow of matter, sparking the formation of galaxies, and orchestrating the grand cosmic ballet across billions of years. The emptiness of the void is an illusion. The darkness is not an absence of things, but a presence of things we are not yet fully equipped to see. It is filled with the universe's memory, the ghostly remnants of consumed galaxies orbiting in massive halos. It is filled with potential, with vast rivers of pristine gas flowing along cosmic filaments, waiting to be drawn into a galaxy to fuel a new generation of stars. And it is filled with mystery, with galaxies made of an unknown substance that dominates the mass of the universe, and others that seem to defy its existence. Our journey into this phantom universe has only just begun. The instruments of this new era of exploration are switching on, and the data is beginning to pour in. Each new discovery, each faint filament imaged, each ghost galaxy cataloged, deepens our understanding while simultaneously revealing new, more profound questions. What is the fundamental nature of the dark matter particle? Why are some galaxies so rich in it, while others seem to have none at all? Will we ever find a truly starless galaxy? The answers to these questions lie waiting for us, hidden in plain sight, in the vast, silent, and populated darkness between the stars. The universe we thought we knew was just the beginning of the story. The rest of that story, the majority of it, is written in a language of gravity and shadow, a script we are finally learning to read in the echoes of the void.